Welcome to the Math Exploration Tour. Today we are going to discuss a problem which appeared in the entrance exam to Chennai Mathematical Institute this year. This is a problem based on calculus and it is composed of three parts A, B, and C. We are asked to assume that whatever functions are mentioned are differentiable and the circle notation here denotes composition. Let us start. We'll discuss the first part A first. So we have f composed with f equal to f for some function f. And the question asks that then for each x, one must have f prime of x equal to something or f prime of f of x equal to something. So if f of f equal to f, then we have f of x is equal to f of x. And by differentiating both sides, we'll use the chain rule for the left-hand side and we'll get f prime of f of x times f prime of x is actually equal to f prime of x. Now there are two options, either f prime of x is 0 or if it's not 0, then you can cancel it from both sides to get f prime of f of x to be equal to 1. This is the solution to the first part and it's fairly straightforward. Next, we are going to discuss part B of the problem. It says for a non-constant f satisfying f of f equal to f, it is known and you may assume that the range of f must be one of the following forms. That is either R, the closed interval AB, or minus infinity comma B closed, or closed A comma infinity. And we want to show that the range is in fact R. So we are given that f of f equal to f and it's not constant. First, we notice that if x say is a fixed point of f, which means to say that f of x is equal to x is a fixed point of f, i.e. f of x equals x, then x must be contained in the range of f. This is obvious because the preimage of x is x itself. But the crucial observation is that even this is true, which means that if x is in the range of f, then x is a fixed point of f. How do we prove this? Suppose x is in the range of f. Then there exists, this is the symbol for there exists C in R such that f of c is actually equal to x. Now what is f of x? F of x is just going to be f of c. And since f composed f is f, we must have this to be equal to f of c, which is just x, which proves that x is a fixed point of f. Now we want to show that the range of f must be the whole of R. And we have only a finitely many options, which is minus infinity comma b closed, closed a comma infinity, closed a comma b, and R. So suppose for the sake of contradiction, suppose range of f is minus infinity comma b closed. We want to somehow get a contradiction. The best thing you could do now is to perhaps draw a picture. That is, how does the graph of f look? Notice that whenever x is in the range of f, we proved that x is a fixed point. That means If you take the interval minus infinity comma b, for example, the point b could be here, then f would just be the identity function on the whole of minus infinity comma b. Because for each point x in minus infinity comma b, f of x must be equal to x, which says that f must look like this from minus infinity to b. And we do not know how it looks beyond that as of now. What we want is to get a contradiction. How do we get a contradiction? We want to analyze how f looks beyond b. Notice that the range is minus infinity comma b. That means that we can't go beyond b. That means that beyond b, f should either be constant or decrease further. Something like this. There are several options. But notice that now the graph of f at b has a corner, has a corner, which is this, which states, which gives us a hint that f is actually not differentiable at b if this happens. We want to prove this rigorously. So how do we give a rigorous argument? Let us talk about the left derivative of the function f at b, which means that limit h goes to 0 minus f of b plus h minus f of b by h. So this limit as h approaches 0 from the left. This is clearly 1 because the identity function has derivative 1, and for x less than or equal to b, f of x equals x and f is the identity function. But what about limit h goes to 0 plus f of b plus h minus f of b by h? Well, notice that as we can see in the graph, f decreases beyond b and it can't go above b. So for every positive h, f of b plus h must be lesser than or equal to f of b, which means that this limit as h is positive, f of b plus h minus f of b by h must be lesser than or equal to 0. So this limit must also be lesser than or equal to 0. So since the left hand limits and right hand limits are clearly not equal, we can say that limit h goes to 0 plus of f of b plus h minus f of b by h is not equal to limit h goes to 0 minus f of b plus h minus f of b by h. This is the same as saying that since the left hand limit and the right hand limit doesn't exist, the limit has left hand limit and the right hand limit are not equal. Limit h goes to 0 f of b plus h minus f of b by h, which is f prime b, doesn't exist. This shows that f prime b doesn't exist. However, the hypothesis tells us that f is differentiable everywhere, and in particular f is differentiable at b. So this is the contradiction we wanted. This is a contradiction. Now, coming back. So the range cannot be minus infinity comma b closed. Can the range of f be equal to closed a comma b? Clearly not, because the same analysis works. Because the same analysis works as above. Can can the range of f be equal to closed a comma infinity? Well, again, no. It's a symmetric argument. Symmetric argument. You could picture this visually if you draw the graph of f. Somehow we have closed a comma infinity. So suppose a is over here, and then we would have the identity up till a, which means something like this. And then we don't know what we would have identity from a to infinity because that is the range, and we don't know what is the status to the left of a, but whatever it is, it should increase because it can't go below a. The range is closed a comma infinity, so it should either be constant, should either be constant or increase. But again, you sort of have a corner over here, and here the right derivative is going to be 1 and the left derivative is going to be negative. You can check that out, which will again give us a contradiction. So the exact same kind of argument works. So this indeed shows that the range of f must be equal to r, because we had 4 options and we have eliminated 3 of them. And further, the question asks us to prove that there exists a unique such function f. But that is very, very easy now because we know that x is a fixed point. X is a fixed point of f if and only if the range of x is in the range of f. X is in the range of f. But the range of f is just going to be r. So every x is a fixed point, which states that f of x is actually equal to x for every x in R. So f must be the identity function. There's no other choice. So this completes the proof of part B of this problem. Now we come to part C. Part C states that suppose G O G O G is equal to G, which means G composed 3 times as G, and that G O G is a non-constant function. Then it asks us to show that G must be onto, G must be strictly increasing or strictly decreasing, and that there is a unique such increasing G. So we are given G O G O G equal to G, and G O G is non-constant. The idea is to compose G once again and notice something. Now it's clear that if you set H to be equal to GOG, then you have HOH equal to H. Now since G is differentiable, H is differentiable, and H is non-constant by hypothesis. So by applying part B implies that H must be the identity function. Hence, GOG is identity. But that's simply another way of saying that G inverse is equal to G. So G is invertible. We get that G is invertible. This means it's bijective, and hence it must be onto as well. Next part is to show that G is either strictly increasing or strictly decreasing. And we classify both the terms together as monotone. We say that G is monotone, or to be more precise, strictly monotone. So we know that G is continuous. We know that G is continuous, and G is 1-to-1 because G is invertible. We want to show that this in fact implies then G is monotone. So what this actually says is that if you have a graph of a continuous function which is 1, 1, so you must go on increasing if you start increasing. And if you think you can come back, then G cannot be 1 to 1, no, because it fails the horizontal line test. There are 2 points where G attains this particular value. So the idea is to use this geometric intuition. So to formalize this, suppose we have A less than C less than B, and G of A is lesser than or equal to G of C, but is greater than or equal to G of B. So this is one case where it may fail. In this example, we have something like this, where it's not strictly increasing. Another possibility is that we may have something like this. First it's decreasing and then it increased. But without loss of any generality, we are going to assume this particular case. We're going to assume the first case. We're going to assume the first case rather than the second. The argument for the second one would be exactly symmetric. Now further notice that we may remove equality from here because G of A cannot be equal to G of C because of uh, the injectivity of G. So we could just remove equality. So we just need to contradict this particular statement. How do we do that? Whenever we talk about continuous functions, the first thing which appeals to us is the intermediate value theorem. The intermediate value theorem. So it states that if you have a continuous function f, have a continuous function f, and say an interval a comma b, this is the graph of f, and you have f of a and f of b over here, then f attains every intermediate value between f of a and f of b if it's continuous. So more formally, it states that if c is between f of a and f of b, then there surely exists at least one d in AB such that f of d is equal to c. So we are going to use this particular idea over here. Let us visualize the case 1. So you have something like this. Suppose you take a point A, you take a point C over here, and then you take a point B over here. So it's easy to see that A less than C less than B, but G of A is lesser than G of C, and that is greater than G of B. Why is this not possible? We'll just apply IVT, the intermediate value theorem, twice. So suppose we take some value which is between G of C and G of A as well as between G of C and G of B. In other words, you can pick uh, D such that pick D such that G of D is lesser than G of C and D is greater than the maximum of G of A and G of B. There clearly exists such a D because of this condition. G of A lesser than G of C, greater than G of B, strictly greater than. So for this D, so it's clear that this clearly implies that because G of A and G of B are both lesser than max of G of A and G of B, we can say that G of A lesser than D less than G of C, and also G of B less than D less than G of C. So if I apply intermediate value theorem in the interval a comma c, I get 1 point which maps to D, and in the interval C comma B, I get another point which maps to D. And they must be distinct because they are in distinct intervals. And I'm picking the open interval A comma C and open interval C comma B for the intermediate value theorem. So those 2 points must be distinct, and hence this contradicts the point that two distinct points map to D itself, which contradicts the fact that G is 1 to 1. So we get 2 points, one in the interval, one in A comma C, and another in C comma B, and one in C comma B, both which map to D. And this contradicts that G is 1 1. So we have shown that G is in fact monotone, which means it's either strictly increasing or strictly decreasing. It cannot be that it can increase and then decrease, or it decreased and then increased. These two possibilities are not possible, as we have shown rigorously. The next part of the question asks us the following, that if G is strictly increasing, if G is strictly increasing, G is strictly increasing, we want to show that G is unique. But we obviously know a strictly increasing function which actually satisfies the property G equal to G. And that's simply a G of x equal to x. So we know that G of x equal to x satisfies G equal to G. We want to show that this is the only possibility, which means that if G is such a function, we want to show that G of x equal to x for every x. So we are going to make use of G of x equal to x for all x. So start with arbitrary y in R, and we want to show that G of y is y. But since G is onto, we showed that G is onto, there exists an x such that G of x is equal to y. But that means G of y is going to be G of x is equal to x. So you have G of x equal to y and G of y equal to x. So G is actually swapping x and y. But this sort of swapping gives us an intuitive idea that it cannot really be strictly increasing. To be more formal, if x is less than y, what happens is you have G of y is less than G of x, which is not possible for strictly increasing G. Similarly, if x is greater than y, then G of y is greater than G of x. Again, not possible for strictly increasing G. So the only possibility is that x must be equal to y, and hence G of y is equal to G of x equal to y. So for arbitrary y in belonging to R, we have shown that G of y equal to y. which means that G must be the identity map. And the identity map also satisfies our condition G equal to G. And thus, this implies that G of X equal to X is the unique strictly increasing solution. So we have completed the solutions to all the parts of the problem A, B, and C. The only thing we did not do so far is that we want to prove that the range of f must be one of the following forms: R minus infinity comma b closed a comma infinity, or closed a comma closed a comma b. How do we show this? Let us do that now. So we know that f o f equal to f, and first of all, f is actually continuous. F is actually continuous. So we can apply intermediate value theorem again to f. Apply intermediate value theorem to f to conclude that if a comma b are in the range of f, this implies that for all c such that which are between a and b, I mean, I'm assuming a is lesser than b over here. Otherwise, we would swap a and b. So for all c such that a less than c less than b, we have c in the range of f. So this suggests that the range of f must be an interval, either open or closed. So in addition to the uh, forms r minus infinity comma b closed a comma infinity and closed a comma closed b, so we have the following options. In addition, we have the following options. Since we can have open intervals, uh, the options are a comma b closed a comma b closed a comma b open a comma b, or minus infinity comma b open uh, a comma infinity. The other intervals, the closed intervals, and minus infinity comma b closed a comma infinity are all already included in the statement. So we want to show that none of these is actually possible. It's not clear a priori why that is true, but we are going to prove that. So I'm going to just take one case. Suppose we take the case open a comma infinity, case open a comma infinity, and it's clear that open a comma b and open a comma b closed, the same idea will work. And for closed a comma b open and minus infinity comma b open, the symmetric idea will work. Just like how in part B, we gave such similar arguments or symmetric arguments about why just proving for minus infinity comma b would suffice. Why is this not possible? So since a comma infinity, we want to show that a comma infinity cannot be the range of f. So if range of f is a comma infinity, we can say that f of x is actually equal to x for every x greater than a, because x is a fixed point if and only if it is in the range of f, as we have shown. So if you consider this limit h goes to 0 plus of f of a plus h, which means I'm trying to somehow approach a from the left. We want to say that since f is continuous and f of x equal to x for every x greater than a, we also must have equality at a, because for every x greater than a, it's the identity function f of x equal to x, f fixes x. And continuity sort of implies that a also must be a fixed point. That is what we are going to do formally over here. So if you consider this limit, on one side, this is equal to limit h goes to 0 plus of just a plus h, because if h is greater than 0, a plus h is in the range of f, so f of a plus h is equal to a plus h, so this is equal to a. On the other hand, since f is continuous, we can actually take the limit inside and say that f of this is equal to f of limit h goes to 0 plus of a plus h, which is going to be f of a. So this demonstrates equality. F of a must be equal to a, which means that a belongs to the range of f. But that is a contradiction because we assume that range of f is open a comma infinity. So this states that it cannot be, the range of f cannot be open a comma infinity. Similarly, we can say that none of the other cases over here are possible, and therefore the range of f must be one of the forms mentioned in part B. So this is the entire solution to the problem B5, which was asked in the entrance exam to CMI 2023, which happened on 7th May 2023. So I hope the solution is clear, and hope if for more math, please do subscribe to my channel. I'll be coming back with more videos soon. Thank you.